So let's talk about external DSL style. That is a certain style of implementing a domain-specific language. We're going to use the finite state machine language as a running example again. So here's a nice intuitive visual syntax for a turnstile in a meter system. So we've got states and we've got events and actions along the transitions. So what we want to do is we want to implement this time around a textual syntax for finite state machines. Okay, so this could be the textual syntax that we want to support. So we've got like state declarations. Well, we have 3 of them because there are 3 states. So a state declaration consists of the state keyword followed by the name of the state, and in closed braces we've got the transitions for that state or departing from that state. So we use this arrow notation for the transitions. Well, and if there's no arrow, this means it's a self transition, so the target state equals source state. So we also see here that the action is optional, so some of the transitions don't have an action. And of course, all transitions must have an event. And one of the state declarations is marked as initial with this keyword initial. Okay, so this is the textual syntax that we want to implement. And in fact, we want to implement it in a way that we would speak of an external DSL. That is, we are going to have a designated parser. And by the way, maybe also a designated checker for well-formedness, an interpreter. We could even later have a compiler to some target language. So as opposed to going for internal DSL style, which is when we implement a DSL essentially as a library in some other programming language. So we want a designated parser this time. And for this presentation to make sense, you should have studied already the material on internal DSL style, because we sort of built on top of this a little bit. So we're going to do external DSL style with Antler, the parser generator Antler, and Java. So the parser generator Antler takes a parser description and generates some code from it. In our case, we're going to generate Java. Antler can also be used with other target languages. So here is how we get started with the textual syntax. It's a grammar-based concrete syntax definition. So these are productions. So they always have a left-hand side, namely the syntactic category, we say non-terminal, being defined, and they've got a right-hand side after the colon, and that's how the syntactical category is structurally defined. So we just go through the rules. A finite state machine, FSM, is a non-empty sequence of, let's say, state declarations followed by the end of file character. A state declaration then in turn starts with an optional initial keyword followed by a state keyword followed by a state ID followed by open brace followed by possibly empty sequence of transitions, followed by close brace. And then we've got the structure of the transition here. There's an event, possibly an action with the slash, possibly the arrow and a target state ID, and semicolon. State IDs, events, and actions are just names, and names are just sequences of letters. Okay, so this grammar-based approach here, well, we basically adopt what's called the extended Bacchus-Nauer form. Well, it turns out we already used a notation that is supported by Antler, but in fact this is extended Bacchus-Nauer form. So here we see indeed the complete input for the parser generator Antler. So we've got some extra declarations here. So we assign a name to the grammar because that name is useful in generating code, in using this name in the names of generated classes. We have some pragma here a header pragma to basically assign a package to the generated classes. And then down here we have a symbol, a non-terminal we were not yet talking about previously, WS for white space. So basically we regulate what sort of characters may occur between all these things up here, between the keywords and state IDs and all these syntactic structures here. That is, there can be spaces, tops, new lines sort of, in many of them. And here we touch directive skip or in action, which basically means they are going to be skipped already along parsing, so we never have to deal with white space non-terminals up here. Okay, so this is essentially our effective definition of the textual syntax. So here's driver code for an actual syntax checker, which is a component that we can feed with a file name, let's say, pointing to some text, and the main method would just succeed fine if the input text conforms to the textual syntax, or it would exit with a non-zero exit code if there are any syntax errors. So this driver code essentially just uses the generated FSML parser and FSML lexer classes. So the lexer class is the one that, given some textual input, in fact some sort of a file stream, Antler file stream, it will essentially try to recognize tokens, that is keywords like initial and state, special characters like open and close brace, and state IDs. And in fact, we wrap this lexer object in a common token stream object so that we get access to the stream of tokens. And that stream is passed further to the constructed FSML parser object, which is the actual parser that will check the syntax and maybe also on the fly construct a parse tree, a concrete syntax tree. So yeah, so this is just this kind of cascade of object construction to eventually be able to invoke the parser. That is, we invoke the method FSM corresponding to the FSM non-terminal of the grammar. And then we just check that the number of syntax errors, that it presumably equals the number of expected syntax errors. Only then we return a zero exit code. Now, just to make this a little bit more clear, the whole engineering behind it, here's a makefile that does all the involved steps: generation of code, compilation of generated code, and running the parser, or checker for now. So here we've got the jar with Antler. Here we have the invocation for the Antler tool. This is some class with some main method. And in this manner we can invoke the parser generator. And at some point we have this class here. We were just looking at the code, FSML syntax checker. This is our class, our boilerplate code, using the generated code for lexing and parsing. Yes, generation just invokes Antler on a grammar that we have seen. Compilation just compiles all the generated and handwritten Java code. And then we can invoke the syntax checker on some examples, like a positive example and maybe a negative example. Here we don't expect any syntax errors. Here we expect one syntax error. Okay. For now, we can only check that some text conforms to the textual syntax. But of course, we would like to somehow construct what's called an abstract syntax tree, or in our case, some Java objects, so that we can further possess the finite state machine. So, in fact, what we do with Antler is, with the FSML lexer class, we get a scanner that is a mapping from input text to a token stream. And with the FSML parser class, we get a mapping from the token stream to concrete syntax trees. We haven't looked at them yet, but they were sitting there. So what's missing is we somehow have to plug in some functionality for performing abstraction, that is a mapping from concrete to abstract syntax trees. So this is what's going to be of interest here. And if these are suitable objects, maybe just the same objects as we used in the internal DSL style context, well, then we know how to continue from there. So we can write interpreters, well-formed checkers, and all kinds of language-dependent tools on top of such ASTs. Now, one way of performing abstraction, that is CST to AST mapping with Antler, is to use a so-called listener. So the idea is that Antler also generates what's called in FSML base listener. And listener is meant here in the sense of listening to the traversal of a concrete syntax tree. So a listener for FSML basically has enter and exit methods for all syntactic categories. In this manner, we imagine to walk the concrete syntax trees, and we can then, at appropriate points along this walk, we can perform functionality. So in this case, we are interested in doing something when we enter the FSM. Well, we just construct an FSM object. We are interested in doing something when we enter a state declaration. Well, we construct a state object, and we somehow retrieve the state ID from the concrete syntax tree here. And we also add this newly constructed state to the collection of states maintained by the FSM. And likewise, when we enter the transition, then we construct a new transition. We add a transition. We get the source state from the attribute current. We get the event from the syntax tree. We get the action from the syntax tree, and it's optional, so we might not find any action. And we try to find the target state in the syntax tree. If it's not there, we use the current state ID. So this is the way we do it. So we implement these enter FSM, enter state, enter transition methods of the FSML listener. And then we just have to plug this listener somehow into a walking process over the concrete syntax tree. And in this manner, we would construct this FSM object with all the transitions and states. And this is the code that drives parsing, including abstraction. So this time we have like a static method which takes a file name and which returns an FSM. And so you see we again create an Antler file stream, a lexer object, a common token stream, and a parser object, just as before. So we also invoke the FSM method on the parser object. And this time we care about the result. The result is actually a parse tree, which is just another term for concrete syntax tree. And by the way, here we don't want to continue in performing abstraction if there's any syntax errors, so we just insist that there's zero syntax errors. Now we need to construct our listener object. That's the class we were just looking at. And here's a parse tree walker. That's a class provided by Antler. And then we tell the walker, hey, here is some listener to listen to while walking, and this is the tree you should walk. And then the listener, our object, after walking, we can just retrieve the FSM object. And so we are done with parsing text into an object. Well, so a minimum Dsl implementation would be that we somehow define the abstract syntax. Well, we have done this here. We have assumed that we had a suitable object model. And of course, we also wanted to define the concrete textual syntax. So we have done this here by defining a parser based on a grammar notation. And for a minimum DSL, we also should have a dynamic and a static semantics. Now the point here is we will not look into dynamic and static semantics because we have done this already when we discussed internal DSL style. And in fact, we can use exactly the same implementations as we used there because they operate on the object model for abstract syntax. So they are not tied to the textual syntax in any specific way. That's it. All the code for this presentation is in the YAS repository, and FSML is covered in detail in Chapter 2. This includes discussion of internal and external DSL style. Thank you.